Welcome. Today we delve into the core of modern computer-aided design, parametric constraints. What does this term actually mean? At its heart, it represents a fundamental shift from traditional static digital drafting to the creation of intelligent, rule-driven models. Imagine a standard drawing as a simple picture. If you change one line, you must manually adjust every other related line. Parametric modeling changes this entirely. It transforms our CAD files into dynamic systems where every element can be linked through a set of rules. This intelligence is what we call design intent. It's the logic behind your design, the fact that a hole should always be centered or that two walls must always remain parallel. Parametric constraints are the tools that allow us to embed this intent directly into our model. They govern the intricate dance between all the components of a design. The geometry, which forms the shape, the dimensions, which define the size, the annotations, which provide critical information, and even the cross-hatching, which represents materials. These elements no longer exist in isolation. Instead, they interact dynamically. When one aspect is modified, the entire model intelligently adapts to maintain the established rules. This creates a flexible, robust, and less error-prone design process. Understanding this concept is the first step towards unlocking the full potential of advanced CAD systems and revolutionizing how we approach engineering, architecture, and product design. Now that we understand the what of parametric modeling, let's explore the how, starting with geometric constraints. These are the first pillar of parametric design, and they are all about logic and relationships rather than specific numbers. Geometric constraints control the fundamental shape and behavior of your sketch elements. Think of them as the grammatical rules of your design's language. For example, a parallel constraint ensures that two lines will always remain parallel no matter how you stretch, move, or rotate the sketch. A perpendicular constraint locks two lines at a perfect 90-degree angle. A concentric constraint forces two circles or arcs to share the same center point, which is crucial for features like flanges or washers. The tangent constraint creates a smooth, seamless transition between a line and an arc, a vital relationship in designing everything from machine cams to sleek product casings. Other common constraints include symmetric, horizontal, vertical, coincident, and collinear. Each one imposes a specific logical rule that removes ambiguity from the design. By applying these constraints, you are building a robust and predictable geometric skeleton. This framework ensures that the design behaves as intended during subsequent modifications, preventing accidental distortions and maintaining the core integrity of your concept before a single dimension is even added. If geometric constraints form the logical skeleton of our design, then dimensional constraints are the muscles and substance that give it precise form and size. These constraints move us from abstract relationships to concrete measurable values. This is where we define the exact length of a line, the precise angle between two planes, or the specific radius of a curve. These are the numbers that matter for manufacturing and function. A key concept here is the idea of driving versus driven parameters. A driving dimension is one that you explicitly define and which controls the geometry. If you set a width to 100 mm, that is a driving dimension. The model must obey. A driven dimension, on the other hand, is purely for reference. It is a measurement that results from other constraints and cannot be edited directly. The true power of parametric design is unlocked when we use equations and linked variables. You can define one dimension in terms of another. For example, you can create a rule that the height of a bracket must always be half of its length. By setting height equals length by 2, you embed a powerful design rule. Now, if you change the length from 200 mm to 300 mm, the height automatically updates from 100 mm to 150 mm. This capability to build mathematical relationships directly into the model geometry is what makes parametric design so incredibly efficient for creating scalable designs and iterating on new ideas. Applying constraints is not a haphazard process. The goal is to achieve a perfect state of balance and stability. In parametric modeling, sketches can exist in just one of three states: under constraint, fully constrained, or over constrained. An under-constrained sketch is ambiguous and unstable. It has what we call degrees of freedom, meaning parts of the geometry are still free to move in unintended ways. If you were to drag a point on an under-constrained sketch, it might stretch or distort unpredictably, breaking your design intent. It's like a wobbly table with a loose leg. The ideal state is fully constrained. This means you have provided just enough geometric and dimensional constraints to eliminate all degrees of freedom. The sketch is completely defined, stable, and will behave exactly as you expect when changes are made. Its shape and size are locked in. This is the goal for any final design. The third state, over-constraint, is problematic. This occurs when you apply redundant or conflicting constraints. For example, telling a line to be both 50 mm long and 60 mm long at the same time, or telling two lines to be both parallel and perpendicular. The software's mathematical constraint solver, the powerful engine running in the background, cannot resolve this conflict and will flag an error. Understanding and managing these states is a critical skill. It's a process of methodically locking down your design's geometry until it is robust, predictable, and free of conflict.
One of the most profound benefits of a fully constrained parametric model is associativity. This refers to the intelligent bidirectional link between the 3D model and its corresponding 2D manufacturing drawings. In the era of traditional 2D drafting, if a designer changed the model, a draftsperson had to manually find and update every single view, dimension, and note on the drawing, a tedious and extremely error-prone process. Associativity eliminates this problem entirely. The drawing is no longer a separate static entity. It is a living document, a direct reflection of the 3D model. When you modify a feature in the 3D space, say you increase a hole's diameter from 10 mm to 12 mm, the parametric system automatically propagates that change everywhere. The circular feature on the top, front, and side views of your 2D drawing will instantly resize. The dimension annotation will automatically change from reading 10 to 12. Any notes that reference that hole will update. Even complex cross-hatching patterns that denote material will automatically adjust to the new boundaries of the geometry. This powerful, seamless integration ensures that your documentation is always synchronized with the master model. It drastically reduces errors, saves countless hours of manual checking, and provides a single source of truth for the entire design and manufacturing process. Once you've mastered the fundamentals, parametric modeling offers even more powerful tools for managing complex designs. Two of the most important are global variables and design tables. Global variables, sometimes called parameters or expressions, allow you to abstract key values from the sketch and place them in a central editable list. Instead of hard-coding the thickness of a part as 5 mm in 10 different places, you can define a single global variable called material thickness and set it to 5. Then, you simply link those 10 dimensions to this variable. If you need to change the thickness later, you change it in just one place and the entire model, no matter how complex, updates instantly. This is a massive leap in efficiency and control. Design tables take this concept even further. They integrate the power of a spreadsheet directly into your CAD file. Each row in the table can represent a different version or configuration of your model. For example, you could have a single master file for a screw. The design table could have rows for M3, M4, and M5 screws with columns controlling the diameter, length, and thread pitch for each version. By simply selecting a row, you can instantly switch the model to that specific configuration. This is the ultimate tool for creating entire families of parts, managing standard components, and exploring numerous design iterations without ever leaving your primary file. The power of parametric constraints extends far beyond single parts. It's the very foundation of how we design and analyze entire systems. In the context of an assembly, constraints are called mates. These mates define the spatial and motional relationships between different components. A concentric mate aligns a bolt with a hole. A coincident mate makes two surfaces touch. By applying a series of mates, you build a virtual assembly that behaves like its real-world counterpart, allowing you to check for interferences and simulate mechanisms. But modern systems go even deeper by integrating manufacturing tolerances. A part is never manufactured to its exact nominal size. There's always some small variation. Parametric models allow you to define these tolerances, for instance, specifying a shaft's diameter as 20 mm plus or minus 0.05 mm. This enables sophisticated tolerance stack-up analysis where the software calculates the possible cumulative effect of these variations to ensure parts will always assemble correctly. Finally, this rich, intelligent data doesn't end at the design stage. The parametric model becomes the master source for manufacturing. Its precise geometry drives the tool parts for CNC machines, the layers for 3D printers, and the data for robotic assembly lines. In this way, the parametric model evolves from a simple drawing into a complete digital prototype or digital twin that encompasses design, function, and manufacturing intent in one cohesive package. To conclude, we have journeyed through the entire landscape of parametric constraints, from the foundational concepts to their most advanced applications. We started by understanding that parametric modeling transforms static drawings into intelligent, rule-driven systems that capture design intent. We saw how geometric constraints define the logical shape, while dimensional constraints provide the precise size, working together to create stable, fully defined sketches. We explored the revolutionary power of associativity, which creates a living link between our models and drawings, guaranteeing accuracy and saving immense time. Then, we elevated our understanding by examining advanced features like global variables and design tables, which allow for unparalleled control and the efficient creation of entire product families. Finally, we saw how these principles scale up to system-level integration, defining complex assemblies, analyzing manufacturing tolerances, and driving production processes. The key takeaway is this: parametric modeling is not merely a feature set within a CAD program. It is a comprehensive methodology, a paradigm for design thinking. Its benefits are transformative: radically increased efficiency, a dramatic reduction in costly errors, and the agility to innovate and adapt designs with ease. This robust, adaptive approach is precisely why parametric modeling has become the undisputed standard across mechanical engineering, architecture, product design, and countless other disciplines. For any aspiring designer, engineer, or innovator today, a deep understanding of this paradigm is not just an advantage, it is a fundamental and essential skill.